Welcome class to Lecture 2, where we're going to be looking at rotation matrices and learn what SO of n, the special orthogonal matrices of order n, what that means. This is chapters 2.1 and 2.2 out of the Robot Dynamics and Control book. So just to put this in perspective, our goal is to be able to control a robot manipulator with multiple joints and be able to send it to different positions and move at different speeds, and then to get some feedback from the camera. So where we're going to start first today is we're going to think about how can we take our robot and how can we apply coordinate frames to each joint. So imagine I've got a coordinate frame on this joint. As I move my shoulder, this joint is going to move. If I put another coordinate frame here, this coordinate frame moves when I move either my shoulder or my wrist. And so we're going to learn how to represent transformations from one coordinate frame into another coordinate frame today. We want to be able to talk about where is our end effector in a common coordinate system. For instance, usually we want to put a coordinate frame on the ground, the reference frame, that everything else is referenced to. Typically, our robots have these sensors that can measure what is the different angles of each of our joints. And so forward kinematics figures out what is the position orientation of that tool, the end effector, in terms of those joint variables. So in our problem, we want to know where is this end effector. We say that its end effector is a position, we'll just call this x and y. Forward kinematics wants to derive what are those given that we know theta 1, and we know theta 2. And so we've solved this by breaking it up into a simpler problem. First we say, well, what is the position of this point here? Now this is the origin of the frame 1. So we can call this O1x and O1y. And then we say that x is just equal, how far do we go along this? Well, this is r1 times the cosine of theta 1, and this is r1 times the sine of theta 1. And then we need to add in the additional distance, and that additional distance is going to be this r2. We're rotating that by a distance, theta 1 plus the theta 2. And so that's going to be r2 cosine of theta 1 plus theta 2. And this is r2 sine of theta 1 plus theta 2. So much for that review. We also need to talk about, well, what is this orientation frame that we have over here? And what we can do is we can import our rotation matrix, our base frame. We want to know, well, how far have we rotated from there? Well, this distance that we've rotated is theta 1 plus theta 2. And so, but what we want to know is, what are these x positions? This x-axis right here, and what is this y-axis? And so this x-axis, well, we want to know, well, where is x? And I'm going to make it bold just so you know that this is a coordinate frame. What is x2 in the base frame? And then we also want to know, well, what is this y2 in the base frame? And so we do that. We take x2, this line x2, and we project it onto both x1, x0 and y0. So I'm going to project that onto x0, and I'm going to project that onto y0. And then we want to do the same thing with my y2. I want to project that onto the y and onto the x. And so that is x0, y0. When we do the math for that, this projection here was just a cosine of both the angles, theta 1 plus theta 2. Whereas this is the sine of theta 1 plus theta 2. This one up here is negative. So this is the negative sine of theta 1 plus theta 2. Whereas this is the cosine of theta 1 plus theta 2. All of this is forward kinematics. There's 4 regimes. So if I want to put the tip of the robot back at the shoulder joint, turns out there's an infinite number of solutions that can do that. Because as long as theta 2 is equal to pi, then theta 1 can be anything from 0 to 2 pi. The next regime that we have is anything that's within this pink region. Because anything that's in that region I can solve by an elbow up and elbow down position. The next one is right on the edge of our workspace, and there I can only get by having my theta to be exactly 0. Theta 2 is 0. So there's only one solution for every point along that border. And then anything outside that region is unreachable, and so there are 0 solutions. So 4 different regimes there. So the next thing that we'd like to do is figure out the velocity of the kinematics. And the velocity kinematics says, how fast is this point moving? In what direction is it moving? Here I'm going to use a marker. Is it moving in this direction? What is its velocity in x and y? We do that simply by taking the derivative of our kinematic equations. So that's just dt of my original equation, which was r1 cosine theta 1 plus r2 cosine theta 1 plus theta 2. And this one here is just the ddt of r1 sine theta 1 plus r2 sine theta 1 plus theta 2. Then we can work that out, and when we work that out, we're just identifying which things can change. Since this is a rotational joint, the only thing that can change are these rotational joints. And so we take the chain rule and figure out what happens when I change theta 1. If I work that out here, then I'm going to have, so that is just negative r1 sine of theta 1, and that quantity is times theta 1 dot minus r2 sine of the sum of these two, theta 1 plus theta 2, times the quantity theta 1 dot plus theta 2 dot. And very similar to the other side, it'll be r1 cosine theta 1 dot plus r2 cosine theta 1 plus theta 2 times theta 1 dot plus theta 2 dot. And that is our velocity kinematics. It tells you if I change these velocities, theta 1 and theta 2, how fast do I get my end effector to move in x and y? If we want to invert that, what we did is we took something called the Jacobian, which was the first order derivatives, and that represents how with changing velocities change our end effector velocities. And so if we want to go the other way, then we just take the transpose J inverse times x dot, if this is invertible. And in this case, the inversion isn't too hard to write out. We derive that as r1, r2 sine theta 2 times, we just took this the original Jacobian, and we flipped these and inverted the signs on this diagonal. So this is the story, and this will always give us some numbers. These dA, negative b, negative c, these are always numbers. Remember, we're going to multiply it times some desired x velocity. So maybe we'll say I want my x dot to equal negative 2 and 4. Well, we just multiply this through here, and it tells us exactly how fast our joints need to move, unless we can't multiply it. And when can we not multiply that? Remember, computers are good at many things, but what they can't do is you can't divide by a 0. And that is equal to bad result. And so what we need to do is figure out when is this quantity here equal to 0. There's a few things that it can be equal to 0. If r1 equals 0 or r2 equals 0, but those are trivial cases. If that's what happens with your robot, then you built your robot wrong. But the thing that can change is this sine of theta 2. So sine of theta 2 is equal to 0, and that happens if theta 2 is equal to 0, or if it's equal to pi or negative pi. So basically, if theta 2 is equal to k times pi, where k is in the set of integers, then we have a problem. And what does this correspond to? Well, if theta 2 is 0, that means that my robot arm looks something like this. I've got my robot here, and its first joint comes out to here, and then this angle here, that's theta 1. But if it's 0, then I'm either pointed out this way, or I'm sitting here and I've got the first joint here, and then I've rotated back, and so the next joint is facing this way. And everything else is just cycles of these things. Both of those, I get in this degenerate pose. And you can think about it with your arm. If I stick your arm straight out in front of you, now if I move my shoulder and my elbow joint, they both are going to get rotation that's moving back and forth in the plane. I can't instantaneously generate my velocity backwards by those two. I'd have to do them together in order to make that happen. And I also cannot extend my hand out any farther. I'm locked. I can't go any farther in front. Here's that singular configurations with the full math in there. So when you think about geometry, there's two approaches. One that's called the synthetic approach, where we reason about geometric entities by talking about properties of points and lines. And then there's an analytic approach, where we attach some numbers so we can reason things with algebraic manipulation. In order to do this, we have to affix coordinate frames. And so we have to bolt the coordinate frames in different places in a workspace, and then we can reason with equations and coordinates about this. And so here I have two different coordinate frames. You'll see that there is this 0 coordinate frame, x0, y0, and then there is a second coordinate frame, x1, y1. And then there's this point P that we want to talk about. And we can talk about P by talking about a vector that goes from the origin of the 0th coordinate frame towards P, and we'll call that V1. Or we could talk about some vector that goes from the origin of coordinate frame 1 and goes to P. So there's two different ways that we could talk about P, just like we could have two different perspectives, and both of them are locally correct according to their reference frame. And so what we're doing is we are assigning a coordinate frame. And so here in blue, I'm showing this coordinate frame. And if we want to talk about, in this class, we'll use a subscript convention so that we know which item we're talking about. If there are more than one of a certain label, we'll give them unique numbers. And then the superscript tells us which coordinate frame we're talking about. And so if I want to talk about P in coordinate frame 0, I am going to put a superscript saying that I'm talking about coordinate frame 0. And then I just count. That's 1, 2, 3, 4, 5 in X, and 1, 2, 3, 4, 5, 6 in Y. And then if I want to talk about the origin of this next frame, that's just about exactly 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 5 upwards in there. And so we can talk about coordinate frame. Which coordinate frame origin are we talking about? Well, we're talking about coordinate frame 1, so this point here, in frame 0, is at 5 and 10. However, coordinate frame 01 in frame 1 would be 0, 0. Now we can also do the same trick. We can say, well, coordinate frame 1 is the one I care about, and I want to know, well, what is P in that? Well, P, if we were talking about P in coordinate frame 1, well, we're going to go negative in that x direction, 1 to 2.8. And then we're going to go positive in this y coordinate, 1, 2, 3, 4.2, gives us a location of P. And then we can also talk about what is the location of this origin. Well, to find that, we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.6. That gives us our x location, and then we're going up 1, 2, 3, about 3.5 to get this point. And so both of them are valid ways. We're talking about where is the origin of frame 0 in coordinate frame 1. The two valid ways of talking about it. Now we can also do the same thing with our vectors. However, vectors are free vectors, meaning that you can slide them around. And so I can take this vector v1, and if I want to know what is it in frame 1, I have to slide it over to the origin over here. So if we're talking about v1, v1 is this orange line, and I want to know what it is in frame 0, well, that's just a location of P. That's 5, 6. But if I want to know v1 in frame 1, I have to take this orange vector, translate it all the way over to the origin over here, and then count. And it's 1, 2, 3, 4, 5, 6, 7.7, and about 0.8 upwards. And so that is its value in coordinate frame 1. And I can do the same thing with v2. If I want to talk about v2 in coordinate frame 0, I have to transpose it until it's at the origin, and then I can just count where it is. It's in the negative direction, 5.1, and then upwards 1, whereas in its regular coordinate frame, it's P in frame 1. So that's negative 2.8 and 4.2, just like what we had before. Now let's imagine that our coordinate frame 1 is obtained by rotating our original coordinate frame by theta. I've got a wonderful illustration of that. I'm just going to take my coordinate frame and I'm going to rotate 1. And that's the difference by theta degrees. And so if we wanted to represent that numerically, we could represent that with a scalar number called the angle theta. And that seems like a nice mathematical solution. However, there's a problem. There's a discontinuity when we go all the way 0 to pi over 2 to when we come to 2 pi, it goes suddenly from 2 pi to 0. And there's this discontinuity in there. And that's numerically, it causes problems because if we take a derivative of that, we suddenly get this discontinuity. We'd like not to do that. The other reason not to just represent it by an angle is it becomes very difficult to then take that into 3 dimensions. Again, we're going to have some discontinuities. We want a consistent way to be able to represent rotations in multiple directions. And so instead of just representing it by a single number, we're going to represent, and even in 2D, by 4 numbers. And what we're going to do is we're going to say, what is this vector x1 in frame 0, and what is a vector y1 in frame 0. And this matrix that we construct by we're telling where are these new coordinate frames is going to be in this 2x2 matrix in 2D and 3x3 in 3D, and that is a rotation matrix. And they have wonderful properties. So we want to prove that the dot product is commutative. We just show that this gives you AE plus BF plus CG. And this dot product of these two vectors, 3x1 vectors, I get EA plus FB plus GC. And you'll notice that all I'm doing is swapping these, and since multiplication is commutative, these are equivalent. And so if I have a rotation matrix, I have R1 in frame 0. That gives me these projections, these 4 projections. If I take the transpose of that, what do I get? Let's work that out. So I just copy the diagonals, x1.x0, y1.y0, and then I'm going to flip the right diagonal. And so this one will be x1.y0. This one is y1.x0. And so since this dot product is commutative, I can swap the order of these two, and I'm going to go ahead and do that. So this is x0.x1, and here is x0.y1. And then this next term that I have over here, this is y0.x1, and this is y0.y1. So if you look at this, this is really what is my x0 vector in terms of frame 1. And this next term over here is what is my y0 in terms of frame 1. This is just what is R01. And so we have shown that the transpose gives the inverse here of this rotation matrix, which is a pretty cool idea. A true rotation matrix, the column vectors are unit length, and they are mutually orthogonal. That means that the matrix itself is orthogonal. Some cool properties that we have here. If we take the transpose of a rotation matrix and multiply it by itself, then we get the identity matrix because the transpose is the inverse. So the transpose of R10 is the inverse. Now it's important that we understand this superscript convention. In our notation, we're going to say that the subscript is our unique identifier. It's saying, which thing are we talking about is a subscript, whereas a superscript says, who are we referencing this to? So what coordinate frame are we using? And you can drop this unique identifier if it's the only one in the picture. So in the picture we have just P. There's only one P, and so we can talk about either P in frame 0 or P in frame 1. In our case, the P that we have is at position the X is 5 along and the Y is 6. And that the origin, there's 2 origins. So if we can either talk about origin 0 in frame 0, well, that is going to be just at 0, 0. Origin 1 in frame 0 is interesting. And we can measure it. It is 10 in X and then 5 in Y. Now we have 4 beautiful properties for special orthogonal matrices of order n. I think special deserves some script. If we say that R is an Rn, that means that first off, that the transpose of RT is equal to the inverse for any matrix that's in SON. Next off, the columns, and therefore the rows, the rows of R are mutually orthogonal. Next, each column, and therefore each row of R, is a unit vector. And finally, these three properties would not be enough to fully define a rotation matrix. So we declare that the determinant of R is equal to 1. And so if ever you're taking what you think is a rotation matrix and you take the determinant of it, and if you get a -1, then it's a left-handed coordinate system, so it's not a valid. We're going to say that all of our rotation matrices are right-handed coordinate frames. Now when we move into 3 dimensions, we're just going to say, what is my vector x1 in frame 0? What is my vector y1 in frame 0? And what is my vector z1 in frame 0? And so here's our first simple explanation. If I take my coordinate frame and then I rotate it about the z-axis, you notice that the z doesn't change at all. And since it doesn't change at all, you can see over here in this matrix that it's just 0, 0, 1. It's constant. Whereas my x and my y are the same rotation that we saw in 2D. We're just taking our sine or cosine as we rotate that out. So that's our first basic rotation matrix. And this rotation matrix has 3 properties that are beautiful about it. First, if you rotate it by 0 degrees, you haven't moved at all. And so your rotation matrix is the identity matrix. There's been no change on it. Next, if I rotate by theta, and then I rotate additionally by phi, the total rotation is just a rotation about z of theta plus phi. And finally, if I rotate about z by theta, and I want to undo that, I just rotate by z by negative theta. And so the inverse is just moving backwards the same amount that I move forward. Okay, so what we've given here is somebody has given us 2 coordinate frames, and it wants us to come up with a rotation matrix that represents that transformation. So we've got our first coordinate frame, we've got x, y, and z, and you'll notice that now our new z1 is pointed along our original y0, and then our x1 is halfway between x0 and z0. And so one way that you can accomplish that is you can rotate around x0 by a negative pi over 2, and then rotate around your current z by negative pi over 4. So just to see that again, what we're doing is we're rotating around our x by, you can see that we're rotating our x by negative pi over 2, and then we're going to rotate about our current z by negative pi over 4, and we get that. In order to figure out what is this rotation matrix, what we're going to do is just say, well, what is my x1 in terms of the original coordinate frame? What is my y1 in terms of the original coordinate frame? And then what is my z1 in terms of the original coordinate frame? What I really want to know is, what is x1 in frame 0? So here's my x1. I want to know, what is that location? That'll be 3 numbers there. I also want to know, well, what is my y1? And so find that in your frame. Here's my y1. And then finally, I want to know, what is my z1 in frame 0? And here is my z1 coming right out here. And so always go for the easiest one first. I'm going to go ahead and put my breakpoints in here. And the easiest one is that I know that z1 is collinear with y0. And so that means it has 0 component in x0 and 0 component in z0, which means since it's unit magnitude, everything is in this thing. It's pointed along there. So now we have to figure out, well, what can these other ones be? We've been given a hint here, because we're told that this x1 is going to have components in x0 and z0. And so this x1 is going to have something in x and z. It'll have something 0 here. In fact, since we know that this row is going to be unit magnitude, we can put zeros through there. And so if you've got a 45 angle, remember that we have our 45-degree angle, then we've got 1 and 1, and by Pythagorean theorem, the square root of 2 on this side. And so this length over here is going to be 1 over root 2. This distance over here is 1 over root 2. And this x is in 1 over root 2 in the positive x. And it's 1 over root 2 in my z. Now this one, we can also project this over here. This is going to be negative in the z-axis. So negative 1 over root 2. And then it is positive in the x-axis, 1 over root 2. And we have there our solution. And so here's the solution, and you can see that worked out there. They've got 4 beautiful properties. First off, the transpose is the inverse. So I'm bad at doing inverses of regular matrices, but I could almost do a rotation matrix in my sleep. They're beautiful to work that way. All the columns of R are mutually orthogonal. So if I take any 2 columns and I take the dot product of those, I get 0. And also each column and each row is a unit vector. They're of unit length. And finally, the determinant of R is 1. So what we did today is we reviewed what vectors are from linear algebra, and then we talked about how we can represent positions using coordinate frames and how we can represent rotations using coordinate frames again. So what I want you to do is to go to your book and read sections 2.3, 2.4, and 2.7. And I look forward to seeing you next week.